Huh? Okay, good. Um, so now let me share the screen again. Write it down. Dislocation interaction point. Yes. Two-state dislocation can interact. Write down two-state dislocations. Two-state dislocations can interact to have jogs and kinks into dislocation line. Two-state dislocations can have jogs and kinks in the dislocation line. Also, next line, these extra segments in a dislocation line, costs energy. These extra segments in a dislocation line cost energy, and hence it requires work done by external force. Hence, it requires work done by external force. External force tends to hardening of the material. I'll repeat. These extra segments in a dislocation line cost energy, and hence it requires work done by the external force, tends to hardening the material. Okay. So let's start with the first edge-edge interaction. Edge-edge. Okay. So two edge dislocation, if they are interacting together, what will happen? So let's see one edge dislocation. This is the one slip plane. Okay. This is the another slip plane. Okay. And basically you can see this slip plane is, for example, this is your extra half plane, right? And let's say in this case, this is your extra half plane. Try to understand the situation. This is one slip plane. This is the second slip plane. Okay. This is first extra half plane. Okay. And imagine it is moving in a downward direction. So this is your B1, which is the Burger's vector. Okay. This is your extra half plane 2. Then, and it is moving in, let's say, in this direction, maybe. Okay, maybe it is in moving in this direction. Let's call it as a B2. Fine. So maybe imagine it is coming down and it is coming here. Somewhere they will interact with each other, and that is what we are trying to understand. Two Burger's vector, one is downward, one is horizontal, means they are perpendicular to each other. So edge-edge interaction when B1 is perpendicular to B2. So in first case, what we are seeing is B1 perpendicular to B2. What will happen as a result of this? That is what we are going to study now. So draw this figure and I'll explain you what will happen in the next slide. Okay, now what will happen to this edge dislocation? Edge dislocation 1 with the Burgers vector B1 will remain unaffected as B2 is parallel to T1. What is T1? T1 is this. This is your T1, right? Okay, T1 bar is the dislocation line vector. T1 bar and B2 is parallel. So what will happen? I'll show you then the next slide that okay. So basically this B1 bar remains unaffected. Okay, this is Burgers vector B1. So I'll say edge dislocation 1 with Burgers vector B1 remains unaffected as T1 is parallel to T1 is parallel to B2. What will happen to the edge dislocation 2? Edge dislocation 2. See what it is happening. It is like it is trying to cut it down, right? This knife is trying to cut it down. So it will have a jog. Okay, so let me show you how it looks. Okay, so basically this will change the slip plane from 1 to 2 here. Okay, or the parallel slip plane as shown in this here. Okay, this is another slip plane, but this is what the jog is there. Okay, so this is what is happening, and this is your extra half plane. Just okay, this is extra half plane that is remaining as it is. So in the edge dislocation 2 with a Burgers vector B2 what is going to happen? Creates a jog. Okay, or let's say jog occurs. Okay, edge jog in the edge dislocation is of edge characteristic, right? Which is of edge character. Okay, and the length of the jog is equal to magnitude of the Burgers vector of the first dislocation. Okay, so that is where the B1 is taking into the part. Okay, in the same slide you'll get, right? Same location you'll find the recording. Oh, I joined it as 23rd. Okay, yes. So yeah, so today's class is ended, so it will be saved as 23rd class. So but yeah, I will ask them to share you the link to see the recording. Okay, yeah, so write it down. Yes, yes. The online portal itself, you will get the recordings. So now, I hope it is clear that in this case, if two dislocations which are of edge characteristic, edge dislocation, they are crossing or interacting with each other, where B1 is perpendicular to B2, what will happen? Now we'll take an example where B1 is parallel to B2. Okay, write down heading. Edge dislocation, B1 is parallel to B2. Okay, so imagine two slip planes. Okay, so in this case, this is your first dislocation, first extra half plane. Okay, and this is your second extra half plane, right? So this is your, let's say, first slip plane. This is your first extra half plane. In the same way, this is your second slip plane, and this is your second extra half plane. Okay, and this is your Burgers vector B1. Okay, and let's say this is your Burgers vector B2. So now in this case, B1 is parallel to B2, you can clearly see. Yes, yes, I'll give you time to copy. No need to worry. Okay, so B1 is a Burgers vector for the slip on the for the dislocation which is on the slip plane 1, and B2 is the Burgers vector for the dislocation which is on the slip plane 2. So what will happen? Both will get kinked, right? Because dislocation line is perpendicular to the Burgers vector, so both will get kinked. In this case, what is the outcome? Write down, both will get kinked. Both will get kinked. Okay, in detail, if you want to write it down. Burgers, write down everyone. The dislocation 1 with a Burgers vector B1, dislocation 1 with a Burgers vector B1, okay, will get kinked. Okay, and kink is happening in edge dislocation is of screw characteristic, right? Edge dislocation is happening. Okay, in edge dislocation, if kink is happening, it is of screw characteristics, and length of the kink is equal to the magnitude of Burgers vector of second dislocation. Okay, I'll repeat the statement. Edge dislocation 1 with a Burgers vector B1 get kinked, and it is of screw characteristic, and the magnitude of this kink will be equal to B2, which is the magnitude of the Burgers vector 2. In the same way, write down dislocation 2 with a Burgers vector B2 will also get kinked. Edge dislocation 2 with a Burgers vector B2 will also get kinked, again, which is of screw characteristics, and the length of the kink will be magnitude of B1. And the length of the kink is magnitude of B1. Okay. Clear? Can I proceed to the next slide? I'll show you how the figure will look like. Okay, maybe, yeah, can I proceed to the next slide? Yeah, okay, let me know if you want me to stay. So I'll just show you separately to be more clear. Okay, so this was your horizontal plane. Right? So if it gets kinked, means within the same plane, it will move from one point to the another. Okay. So this is how your extra half plane will get kinked. Okay. So this moment is called as kink. Coming towards the vertical one. So basically on the same plane, it gets kinks. Okay, are you following? This is what you can see. If you want to draw, you can draw it. Otherwise, we'll move towards next slide. So this is all about the when we have edge, let's say interaction. Now we'll see edge and screw interaction. If one edge dislocation, another one the screw dislocation, what will happen? And then we'll see edge screw dislocation interaction. Okay, so write it down. Edge screw dislocation. Edge screw dislocation. Okay, let's say edge dislocation with a Burgers vector B1 and screw dislocation to Burgers vector B2, and they are perpendicular to each other in this case. Okay, so let me try to draw the figure so things will be more clear. So this is your slip plane one. In that you have the extra half plane like this. Okay, and it is moving horizontally with a Burgers vector B1. Okay, so this is the first slip plane. This is first extra half plane. Okay, and now we have, imagine we have another slip plane. Let me try to draw it. Okay, like this. And imagine we have the extra half plane here. Okay, extra half plane. Or rather than extra half plane, we can say it's a screw dislocation line with a Burgers vector B2. Okay, so this is a screw dislocation line. Okay, this is a dislocation line. Okay, I hope you are following. We have one screw dislocation line in that Burgers vector is along. So it means that line is basically the dislocation is moving in that direction. Okay. And then we have the B1 for the edge. Now, what will happen because of this? Okay, write down edge dislocation 1, edge dislocation 1 with a Burgers vector B1, with a Burgers vector B1, undergo jog. Okay, undergo jog Okay, undergo jog. And you know, jog in case of edge dislocation is again edge characteristic. So which is of edge characteristic. Edge character. Edge character. And then what is the length of this jog is magnitude of B2. Magnitude of B2 is the length of the jog. Okay. Then about the second dislocation, screw dislocation 2, screw dislocation 2 with the Burger's vector B2, screw dislocation 2 with a Burger's vector B2 undergoes a kink, edge dislocation 2 with a Burger's vector B2 undergoes a kink, and kink in case of screw dislocation is of edge characteristic, and the magnitude of this kink will be equal to magnitude of Burger's vector of 2, second dislocation. Okay, so it's a B2. Just give me a minute. Give me a minute. I'm connecting. Yeah. Yeah, I hope you can see my screen. Yeah. So here, what I was explaining you is when we have screw and edge dislocation, the edge dislocation with Burgers vector B1 undergoes jog, whereas the screw dislocation with the Burgers vector 2 undergoes a um, kink. Okay, let me show you how it looks like. Okay, maybe on the next slide. Jog is happening on the edge dislocation. Jog means changing the slip plane. Okay, and this is your extra half plane. Okay, like this. So you can say this is your extra half plane. And this is jog. Okay, and the magnitude of jog will be equal to B2. And for the kink, this is your extra half plane. Sorry, this is your second slip plane. And basically, this is what it kinks, and this magnitude is B1. Okay. Yeah, that is what I have explained, but just written in the form of the figure. Write down next screw dislocation. When we have screw dislocation. Okay, so when we have two screw dislocations which are interacting, I'll give you one figure first, and then we'll talk about it. Suppose this is your one slip plane. Okay, and let's say imagine this is another slip plane. Okay, and let's say B1 is in this direction, and for this is in this direction. Okay, so this is your B1, and let's say this is your B2. Fine. So imagine these two dislocations. So this is your slip plane 1, and this is Burgers vector B1. This is slip plane 2. So what will happen to the first slip plane? The screw dislocation B1, undergoes jog. Screw dislocation with the Burgers vector B1 undergoes jog. Jog is happening in a screw dislocation is of edge characteristic, and the magnitude of this jog is given by mod of B2. Edge characteristic and magnitude of the jog is given by mod of B2. Same way, the screw dislocation 2 with a Burgers vector V2 also undergoes a jog of edge characteristic, and magnitude of that jog will be mod of B1. So basically, both jogs are happening. Okay. So basically, because of these jogs and all, what is happening? Dislocation is not able to move freely. Okay. and that is nothing. That's why it is increasing the strength of the material. Whenever we study in tomorrow's class, we are going to study the strengthening mechanism, and that is the reason behind it. These jogs and kings, what will happen because of them is they cannot, because of that, dislocation cannot move freely. Okay, dislocation cannot move freely, and it makes the material harder. Okay, so let me show you how it looks. So this is for the horizontal surface, horizontal slip plane. It is undergoing a jog. Jog means out of plane movement. Okay, like this you can imagine. Fine. And if it is for this plane, so this is the one, then it comes out of the plane. Okay, rightward I'm drawing, and then it comes down. So it is not on the plane. So this is basically out of the plane. Out of the plane. Okay. So okay, any doubt till this? Fine. Let me check if some stuff is remain. Yeah. From this, actually, the part which is related to the Miller indices, we are going to study later. Okay, in the physical metallurgy. So I'm not going to teach you now that. After completing this mechanical metallurgy, we will focus on that. Let me close this presentation and open the another one. Okay, I'll just give you an introduction. Maybe not will go in detail, but in tomorrow's class we are going to study these points. Okay. So as of now, I hope you understood with the what is screw edge and mixed dislocation, what is the source and multiplication of the dislocation, how the stress field looks around the dislocation, what are the partial dislocations, and how the dislocation interaction happens. So in tomorrow's session, our focus is mainly to understand the strengthening mechanisms, and to understand that this base was important. So that's why the syllabus is designed in that way, to first understand dislocation theory and then go for the strengthening mechanism. Okay, so in variety of application, we want like our material to be strong enough. Okay, how can you make your material stronger in general? Can you tell me whether in general, let's say you want a stronger material, how will you make it? Either choose the strong material itself, but let's say that is little bit costlier, then what is another alternative you have? Yeah, so yeah, there are a couple of ways to do it. One is the work hardening you can do. Okay. Another one you can make use like precipitation you can do, or grain boundaries you can use, or the you can also use the solid solution strengthening. Okay, so we'll talk about the dislocation motion first. We studied that dislocation is the defect in the crystal. Plastic deformation takes place by this motion of dislocation. That is what we understood. And the ease of dislocation motion decides the strength of the crystal. Okay, this is very important point. If dislocation is able to move very easily inside the crystal, it means that is low strength crystal. But if dislocation is like not able to easily move inside the crystal, then we can say that is stronger crystal, you can say. Okay, so ease of the dislocation motion decides the strength of the material. If it is easy, then its strength is low. If it is getting harder to move inside the crystal, then we can say it as a basically low strength material. Okay. From previous class, what we have studied is clear that lattice itself offers some resistance to the motion of the dislocation, and that is called the PN stress. You remember Peirce-Navarro stress we have studied in the last class, not this class. In the last class, we have studied PN stress we have calculated, and that is the, let's say, you can say minimum amount of stress you have to apply in order to start moving the dislocation inside the lattice. Okay, let me try to bring that maybe. Let me check if it is not this one. Yeah, somewhere down we have, yes, Peirce-Navarro stress. Okay, just a minute. Okay, this one, Peirce-Navarro stress. You remember? So we say this is the minimum shear stress required to move the dislocation to the crystal line is PN stress, and it depends on the material. Okay. Where is that? Just a minute. Yeah, here. Okay, it depends on the B. How much is the distance between two equilibrium positions of the atoms? It also depends on the nu, which is the Poisson's ratio. Okay, then I'll go back to the previous. I'll go back to the current slide, which I'm talking about. Okay, so if that is not enough, okay, if that stress is not enough, that PN stress means friction offered by the lattice is not enough, then we have to create some obstruction to the motion of the dislocation artificially in order to increase the strength of the material. Okay, and that is what the basis for the strengthening mechanism. I hope you understood. Lattice is offering some resistance, but we still want a material to be much more stronger than that. Then we have to make some things such that the motion of the dislocation inside the lattice becomes difficult. Okay, and ultimately that increases the strength of the material. Okay, so how to increase the strength of the material? There are mainly two strategies to strengthen the material or crystal. Completely remove the dislocation. Okay, if you take the perfect crystal, then of course it is like a strong material. Why? Because in that we don't have any dislocation. So dislocation motion will not happen. In order to create the dislocation, you have to apply more stress. Okay, but if it is not perfect crystal, means already some dislocations are there, and the aim is to just move them on the respective slip plane in order to get the plastic deformation. Okay, so one is the completely remove dislocation, but it is very difficult to produce a material without defects. Okay, hence this is not generally used. And the second one is the increase the resistance to the motion of dislocation, means put some things which will obstruct the motion of dislocation. Okay, and that is what we are going to study in this chapter. Okay, and this can be done in many ways, and which is listed in the upcoming slides. So you can clearly see there is a graph, strength of the versus the dislocation density. So basically, as to some point, let's say if you don't have dislocation, you can imagine like how is the you can clearly see in this in the region, sorry, in the left hand part of the graph, that if your dislocation density is low, strength is very, very high. Then strength is go on reducing. Okay, strength is okay. Can you see? I will try to use the laser pointer. Yes, here the dislocation density is low, strength is very, very high. So after some point, what will happen? Dislocation density increasing, strength is reducing. But after again some certain point, as dislocation density increases, strength increases. This is very difficult to do because it's like a completely removing the dislocations is very, very difficult. So we will not focus on this part. We should focus on this part where, like, how can we still increase the dislocation density is one way, okay, of increasing the strength of the material. So dislocation interactions we have to increase. This kings and jogs are, let's say, again avoiding the dislocation motion with each other and causing the material to get stronger. Okay, so that is one way, and the other ways are like to put some obstruction or resistance to the motion of dislocation. Okay, and yeah, I think that's all for today. Maybe we can end our session here, and these four mechanisms which will use to increase the strength of the material, we will study in the next class. Okay, I'll just write the names. You can also write, and then we will end. The first one is solid solution. Okay, making a solid solution, what will happen? There are two kinds of solid solution: interstitial solid solution and substitutional solid solutions. Okay, what they will do, because of them, maybe some, let's say, some solute atoms are bigger, some solute atoms are smaller. So automatically your lattice will get disturbed, and it will create the compressive stress field and the tensile stress field, and that stress field interacts with the dislocation stress field and cancel out each other. Okay, and then it can, let's say, basically obstruct the motion. That is one part which we'll study how basically it is helping. Second one is a precipitate. If you add the precipitate, dislocation is moving on the slip plane, the precipitate is trying to obstruct the motion. So that is second part we'll study in detail tomorrow. Then forest dislocations. If you increase the number of dislocation itself, the interactions will increase and they will lock each other. That is one way. And the third way is the grain boundaries. If we increase the grain boundaries, what will happen is for the dislocation to move, it acts as a barrier, and then again crystal becomes, you can say, stronger. Okay, so these are the four ways: solid solution strengthening, precipitation, forest dislocation, and the grain boundary. Okay, so in tomorrow's class we are going to study these four in more detail. Okay, and then if time permits, we'll start the fatigue chapter. Okay, so that's all for today. Thank you all for joining the class, and try to attend. Okay,